is an events break in calculus on the topic of symmetry and intercepts. So let's first take a look at symmetry. And we'll look at the different types of symmetry. So we have first symmetry about the x-axis, or sometimes it's referred to as with respect to the x-axis. So here's a graph. Here's our x-axis right here. You can see it's the same above and below the x-axis, like a mirror reflecting across the x-axis. So it's symmetrical about that. And what happens when that's symmetrical about the x-axis, for every point x, y, you've got a corresponding point x negative y. I'll put in specific coordinates so you can see. Let's say this one had the point, you can see it doesn't go right through it, but let's say it had the point 1, 3 here. Then it would also, so if it's symmetrical with the x-axis, have the point where the x coordinate is the same, 1, and the y coordinate is the opposite, negative 3. Down here. So the technique then for figuring out if an equation is symmetrical about the x-axis, if you don't have its graph, is you just substitute in negative y for y. Okay? So you plug in negative y for y and into the equation. If this yields an equivalent equation, so if the equation stays the same, then it is symmetrical about the x-axis. Negative y and y should both give you the same x value, essentially. Now let's look at symmetry about the y-axis, or with respect to the y-axis. On this one, you can see if it's symmetrical about the y-axis. Here's our y-axis here. It's like a mirror across the y-axis. This time, for every point xy, there's a corresponding point negative xy. For this time, the y-coordinate is the same, but the x-coordinate is the opposite. So again, it doesn't go through this point, but let's say I went through the point 1, 2 here. Then if it's symmetrical about the y-axis, then it would also have to go through the point negative 1, 2. So this time the x-coordinate is the opposite, and the y-coordinate stays the same. So this is a similar test here. To test for symmetry about the y-axis, you substitute in negative x for x into the equation. If this yields an equivalent equation, then it is symmetric about the y-axis. So you substitute in negative x wherever you have x. If it stays the same, gives you the same y value, essentially, then you know it's symmetrical about the y-axis. The last type of symmetry we're going to look at is symmetry about the origin. Okay? This one's a little bit different, or sometimes referred to with respect to the origin. This time it's a little harder to visualize this, but a graph kind of like sine or cosine, like this, or actually not cosine, but sine, is kind of like this. You can see this time both coordinates are the opposite. So it's like reflecting about both axes. So if you flip this down here about the x-axis and then flip it across here to the y-axis. Because here, if you, let's say we have the point, let's say I went through the point 3, 2 here. Then that would mean if it's symmetrical about the origin, it would also go through the point negative 3, negative 2, where both the x and y coordinates are opposite. That's what it means to be symmetrical about the origin. Okay, so it says for every point x, y on the graph, there's a point negative x, negative y on the graph. So it's kind of like putting the x and y axis symmetry test together. The test for symmetry about the origin, you substitute in negative x for x, and negative y for y. And if this yields an equivalent equation, then it's symmetrical about the origin. All right, now let's take a look at an example of how we do this. So it says check for symmetry with respect to each axis and the origin. So let's just go in the same order we looked at it. Let's test for the x-axis first. So for the x-axis test, wherever there's a, if you look back here, wherever there's a y, you replace it with negative y and see if it stays the same. So if you had a y right there, so if you got x, replace that with negative y, minus the square root of 4 minus x squared. In this case, that's the only y, equals 0. So that gives you, when you simplify it, negative xy minus the square root of 4 minus x squared equals 0. So then you compare this to the original equation. Is it the same or not? You can see this term stays the same, but this one is the opposite sign. So this is not the same as our original equation. So it's not symmetrical about x-axis. All right, now let's check for the y-axis. For the y-axis, remember, what has to be true is we substitute negative x for x, and the y should stay the same. So the equation should stay the same. If we replace wherever there's an x, we replace it with negative x. So let's go ahead and do that. Here's an x, so we replace that with negative x. And replace this x with negative x as well. Squared, and then simplify it. So negative x times y is negative xy minus the square root of 4 minus negative x squared is just x squared, right? So negative plus negative 1 squared is positive 1, so that negative stays out front like that. So you can compare this to the original one. Again, the first term is the opposite sign, the second term is the same sign, so it's not the same. As our original one. So this one is also not symmetrical about the y-axis. Finally, let's just test the origin, see if it's symmetrical about the origin. So to test if it's symmetrical about the origin, remember you replace the x with negative x and the y with negative y. So it's like doing these two tests together in a sense for x and y. So you replace the x with negative x, replace the y with negative y, and replace this x with negative x. So we get, I'm going to simplify that, negative x times negative y is xy minus the square root of 4 minus negative x squared is just x squared, because negative 1 squared is just positive 1. So this time, if we compare this to the original, it is the same as original. Or sometimes when it's the same, what you'll find, not on this particular problem, but you'll find that if every term is the opposite sign, so if this had been negative and this had been positive, that would also be the same because it's just like multiplying the whole equation by negative 1. Which really is the same equation. Notice on the previous two problems, it didn't work that way. The first term was the opposite sign, but the second term was the same sign. So those are not the same. But this one is the same as that, so we know this one is symmetrical about the origin. Now, what can happen sometimes is if it's not symmetrical about any of these three, then you can say there's no symmetry to it. Okay, that can happen. It doesn't have to be symmetrical about one of these three. But in this case, it is symmetrical about the origin. And occasionally you get things that are symmetrical about more than one thing. In other words, if you had a circle that was centered at the origin, you can see that would be symmetrical about the x-axis, the y-axis, and the origin. So occasionally you can get things that are symmetrical about more than one of these. All right. Now let's take a look at intercepts, x and y intercepts. So the technique works for any equation. If you're finding the x-intercepts, you know the y-coordinate has to be 0. You look back at our graphs here, where it intersects the x-axis, in this case negative 3, 0. You can see anywhere it's on the x-axis that's 1, 0, 2, 0, 3, 0, 4, 0, negative 1, 0, negative 2, 0, negative 3, 0. Notice what they have in common is the y-coordinate is always 0. So that's why when you're finding the x-intercepts, you always set y equal to 0 and then solve for x. And in a similar way to find the y-intercepts, these are where the graph touches the y-axis. So that what the y-intercepts all have in common, like this point 0, negative 1 is a y-intercept. So 0, negative 2, 0, negative 3, 0, 0, 0, 1, 0, 2. Notice they all have an x-coordinate of 0, because it's on the line x equals 0. So that's why when you're finding y-intercepts, you know the x-coordinate has to be 0. So you set x equal to 0 and solve it for y. And that works for any equation. They don't have to be functions. Or for anything. Find x, y-intercepts. So the examples here say find the x and y intercepts for each of the following. All right. So you can start with either one. Let's say we start with, the same word here, I'll just abbreviate here, with x intercepts. So we let y equal 0. Now there's different ways to go from here. You could multiply it all out if you want, or I think in this case it might be easier to just add the 4 to both sides. And you get rid of the squared, take the square root of both sides. But again, remember, whenever you take the even root of both sides, you need plus or minus. So square root of 4 is 2, so we get plus or minus 2 equals square root and the square cancel out, x plus 3. So either there's two possibilities here, x plus 3, let's split it up, could either equal positive 2, or x plus 3 could equal negative 2. And when we solve that, we get x subtract the 3 gives you negative 1, and x equals subtract the 3 gives you negative 5. So sometimes you'll see x-intercepts written like this, but it's really not the best way to write them because these can often be confused with vertical lines. It would be x equals negative 1, x equals negative 5. So to make it very clear, you're talking about points, not vertical lines. That's right. Remember, we let y equal 0. So negative 1, 0 is one x-intercept. And negative 5, 0 is the other x-intercept. Okay, so those are x-intercepts. Now let's see if this has any y-intercepts. To find the y-intercepts, we let x equal 0. So one solve for y. Y equals 0 plus 3 squared minus 1. And just solve this for y. So here's just a matter of simplifying it because the y is already by itself. That's 3 squared gives you 9 minus 4. So y would equal 5. But again, even though sometimes you'll see y-intercepts written like this, y equals 5, that's not the best way to write it because y equals 5 really represents a horizontal line. But we're talking about an intercept, which is a point, not a line. So the best way to write it again, we know x is 0, that's what we plugged in, and we just figured out the y coordinate is 5. So 0, 5, that's our y-intercept. In this case, there's only one. So this graph has 2 x-intercepts and 1 y-intercept. All right, let's take a look at another one here. So on this one, we want to find the x-intercepts. Let's let y equals 0. So we have x squared plus x squared times, sorry, x is 0, yeah, there it is, plus 3 times 0 minus 4 equals 0. So the 0 wipes out a lot here. The 0 is for y. Wipes out the second and third term, so we're just left with x squared minus 4 equals 0. You can solve this by adding the 4 and taking the square to both sides, or you could solve, I'm just going to solve it by factoring. You factor in difference of perfect squares, x minus 2 and x plus 2. And set each of those equal to 0. You can see this one will give you x equals 2, this one will give you x equals negative 2. But again, we're not finding vertical lines here, we're finding intercepts, so this would be the point 2, 0, and this would be the point negative 2, 0. So this one has 2 x-intercepts. And then to find the y-intercepts, we'll let x equals 0. So that'd be 0 squared plus 0 squared times y plus 3y minus 4 equals 0. So 0 wipes out the first two terms. We get 3y minus 4 equals 0. You can add over the 4. 3y equals 4. Divide by 3. So y equals 4/3. So you don't always have to get integers here. Again, it's not a horizontal line we're finding. So y-intercept, we let x equal 0. So the y-intercept is 0 4/3. And you're not always going to get 2 x-intercepts and 1 y-intercept. That just happened to be the case on these two equations. And that concludes the notes for AP Calculus on the topics of symmetry and intercepts.